the city's unseen heartbeat. Did you know that in a major city, a water pipe bursts, on average, every 2 minutes? This happens day and night. We only notice when the water stops from our tap, or when a street floods on the evening news. This small, constant failure points to a larger truth. Cities are more than buildings and roads. They are living, breathing organisms. A visible skin, and beneath it, a complex network of hidden machines. These machines are the city's true heartbeat, working silently. They deliver our water. They power our lights. They take away our waste. These parts are easy to overlook. We take them for granted. First, we examine the visible problem, then the hidden mechanism behind it, and finally the system effect almost nobody sees coming. Let us begin with a common city problem, a traffic jam. We have all been there. The surface explanation is simple. There are too many cars on the road. If there were fewer, traffic would flow. However, this is incomplete. Building more lanes often leads to induced demand. A wider, faster road encourages more people to drive, even to live farther or abandon transit. Soon the new road is just as congested. The jam is a symptom, not the disease. To find the hidden cause, look beyond the cars, to the design of the network. Like a river, flow depends on channels. Roads behave the same way. Signals, parking, and where jobs and shopping sit all shape congestion. Together, they create the conditions for jams to form. The visible problem at home: you turn the handle, no water. If neighbors have it too, the cause is not your house. It lives in the wider system, a burst main miles away, or a pump down during a power outage. A simple symptom, a hidden failure in a complex distributed machine. Quick pause. If this helps you see your city more clearly, like, comment, and subscribe to System Atlas for more evidence-based breakdowns. Next, the hard limits that quietly govern every hidden machine. The limits of our tangible world. A water pipe has a certain diameter. It can only carry so much per second. Push harder, and pressure rises to dangerous levels. A power line has a maximum amperage. Exceed it, and wires overheat and fail. These are not opinions. They are laws of physics, engineering that defines absolute capacity. Limits stay invisible until they are reached. As cities grow, more buildings connect to the same old pipes. Then one day, stormwater plus sewage exceeds capacity. At the bottleneck, the flow can't pass. The system overflows, flooded streets, backed up basements. A road lane handles about 2,000 cars per hour before flow breaks down. Near the limit, a small brake tap can send a wave back for miles. At threshold, resilience is low. Small shocks create big jams. Fixes that ignore constraints rarely work. Beyond pipes and wires, another force shapes cities: human incentives. People and businesses respond to costs, benefits, and rules. If electricity is cheap during the day, appliances run then. If parking is free, more people drive alone. These are rational responses to system incentives. Sorting rules manage waste flows and landfill strain. If penalties are weak or sorting is hard, contamination rises, costs climb, landfills fill. Low water prices encourage high use. Lawns watered, long showers, leaks ignored. Tiered pricing creates a direct incentive to conserve, easing strain on supply. Good service attracts riders, grows revenue, funds better service. A positive feedback loop. The reverse is also true. One of the least understood features of city systems is delay. A new subway can take 10 or 20 years from decision to first train. Meanwhile, the city grows, and the original problem escalates. By opening day, the solution can already be undersized. Delays also hide growing risks. Small leaks erode soil for months or years until a sudden failure. Power planning lags shrink safety margins. A heat wave pushes demand past the edge. Managing delays requires foresight, investing well before crises arrive. City systems often behave non-linearly. A small change may not produce a small result. Many systems have thresholds: below them stable, above them a different state. Add just a few cars per minute near capacity, and a highway becomes a parking lot. A bridge designed for a max load can fracture when a small excess crosses the line. Bandwidth holds, until a spike passes threshold and the network collapses into congestion. So engineers build margins of safety, capacity beyond the expected load. Buffers absorb spikes. As cities age and grow, that margin erodes. Systems drift toward tipping points. The key question is not only performance today, but how close we are to the breaking point. Cities are a system of systems, interconnected power, water, transportation, and communications. A power outage darkens signals, stalls pumps, lowers water pressure, and silences towers. A burst main can flood a station, push commuters to roads, and damage buried cables. A storm can halt trash pickup and keep operators from critical facilities. Resilience comes from redundancy, backup generators, multiple pumps and mains. It adds cost, but it stops small failures from cascading. If you value clear, mechanism-first documentaries, like, comment, and subscribe to System Atlas. It helps others find this analysis. The visible world of the city is the end result of its invisible systems. A congested street is rarely just about that place. Lasting fixes target structure, not symptoms. See the whole system: incentives, delays, thresholds, and buffers. What is the one system in your city you rely on most, yet think about least? Cities depend on invisible systems because constraints, incentives, delays, and feedbacks live beneath the surface and shape what we see every day. You've been watching System Atlas, exploring how the world's systems really work. Share your comments below. See you in our next episode.